A network, in the context of electronics, is a collection of interconnected components. Network analysis is the process of finding the voltages across, and the currents through, every component in the network. There are many different techniques for calculating these values. However, for the most part, the applied technique assumes that the components of the network are all linear. The methods described in this article are only applicable to linear network analysis, except where explicitly stated. Definitions. Equivalent circuits. A useful procedure in network analysis is to simplify the network by reducing the number of components. This can be done by replacing the actual components with other notional components that have the same effect. A particular technique might directly reduce the number of components, for instance by combining impedances in series. On the other hand, it might merely change the form into one in which the components can be reduced in a later operation. For instance, one might transform a voltage generator into a current generator using Norton's theorem in order to be able to later combine the internal resistance of the generator with a parallel impedance load. A resistive circuit is a circuit containing only resistors, ideal current sources, and ideal voltage sources. If the sources are constant sources, the result is a DC circuit. Analysis of a circuit consists of solving for the voltages and currents present in the circuit. The solution principles outlined here also apply to phasor analysis of AC circuits. Two circuits are said to be equivalent with respect to a pair of terminals if the voltage across the terminals and current through the terminals for one network have the same relationship as the voltage and current at the terminals of the other network. If implies for all values of, then with respect to terminals AB and XY, circuit 1 and circuit 2 are equivalent. The above is a sufficient definition for a one-port network. For more than one port, then it must be defined that the currents and voltages between all pairs of corresponding ports must bear the same relationship. For instance, star and delta networks are effectively three-port networks and hence require three simultaneous equations to fully specify their equivalence. Equals impedances in series and in parallel equals. Any two-terminal network of impedances can eventually be reduced to a single impedance by successive applications of impedances in series or impedances in parallel. Impedances in series, impedances in parallel, the above simplified for only two impedances in parallel. Equals delta Y transformation equals. A network of impedances with more than two terminals cannot be reduced to a single impedance equivalent circuit. An n-terminal network can, at best, be reduced to n impedances. For a three-terminal network, the three impedances can be expressed as a three-node delta network or four-node star network. These two networks are equivalent and the transformations between them are given below. A general network with an arbitrary number of nodes cannot be reduced to the minimum number of impedances using only series and parallel combinations. In general, Yi and IY transformations must also be used. For some networks the extension of Yi to star polygon transformations may also be required. For equivalence, the impedances between any pair of terminals must be the same for both networks, resulting in a set of three simultaneous equations. The equations below are expressed as resistances but apply equally to the general case with impedances. Delta to star transformation equations. Star to delta transformation equations. Equals general form of network node elimination equals. The star to delta and series resistor transformations are special cases of the general resistor network node elimination algorithm. Any node connected by resistors to nodes 1n can be replaced by resistors interconnecting the remaining nodes. The resistance between any two nodes and is given by. For a star to delta this reduces to. For a series reduction this reduces to. For a dangling resistor it results in the elimination of the resistor because. Equals source transformation equals. A generator with an internal impedance can be represented as either an ideal voltage generator or an ideal current generator plus the impedance. These two forms are equivalent and the transformations are given below. If the two networks are equivalent with respect to terminals AB, then V and I must be identical for both networks. Thus, or, Norton's theorem states that any two-terminal network can be reduced to an ideal current generator and a parallel impedance. Thevenin's theorem states that any two-terminal network can be reduced to an ideal voltage generator plus a series impedance. Simple networks. Some very simple networks can be analyzed without the need to apply the more systematic approaches. Voltage division of series components equals. Consider n impedances that are connected in series. The voltage across any impedance is equals current division of parallel components equals. Consider n impedances that are connected in parallel. The current through any impedance is 4. Special case, current division of two parallel components. Nodal analysis. 1. Label all nodes in the circuit. Arbitrarily select any node as reference. 2. Define a voltage variable from every remaining node to the reference. These voltage variables must be defined as voltage rises with respect to the reference node. 3. Write a KCL equation for every node except the reference. 4. Solve the resulting system of equations. Mesh analysis. Mesh a loop that does not contain an inner loop. 1. Count the number of a window panes in the circuit. Assign a mesh current to each window pane. 2. Write a KVL equation for every mesh whose current is unknown. 3. Solve the resulting equations. Superposition. In this method, the effect of each generator in turn is calculated. All the generators other than the one being considered are removed and either short-circuited in the case of voltage generators or open-circuited in the case of current generators. The total current through or the total voltage across a particular branch is then calculated by summing all the individual currents or voltages. There is an underlying assumption to this method that the total current or voltage is a linear superposition of its parts. Therefore, the method cannot be used if nonlinear components are present. Note that mesh analysis and node analysis also implicitly use superposition, so these two are only applicable to linear circuits. Superposition cannot be used to find total power consumed by elements even in linear circuits. Power varies according to the square of total voltage or current, and the square of the sum is not generally equal to the sum of the squares. Choice of method. Choice of method is to some extent a matter of taste. If the network is particularly simple or only a specific current or voltage is required, then ad hoc application of some simple equivalent circuits may yield the answer without recourse to the more systematic methods. Nodal analysis, the number of voltage variables, and hence simultaneous equations to solve, equals the number of nodes minus 1. Every voltage source connected to the reference node reduces the number of unknowns and equations by 1. Mesh analysis, the number of current variables, and hence simultaneous equations to solve, equals the number of meshes. Every current source in a mesh reduces the number of unknowns by 1. Mesh analysis can only be used with networks which can be drawn as a planar network, that is, with no crossing components. Superposition is possibly the most conceptually simple method, but rapidly leads to a large number of equations and messy impedance combinations as the network becomes larger. Transfer function. A transfer function expresses the relationship between an input and an output of a network. For resistive networks, this will always be a simple real number or an expression which boils down to a real number. Resistive networks are represented by a system of simultaneous algebraic equations. However, in the general case of linear networks, the network is represented by a system of simultaneous linear differential equations. In network analysis, rather than use the differential equations directly, it is usual practice to carry out a Laplace transform on them first and then express the result in terms of the Laplace parameter S, which in general is complex. This is described as working in the S domain. Working with the equations directly would be described as working in the time domain because the results would be expressed as time-varying quantities. The Laplace transform is the mathematical method of transforming between the S domain and the T domain. This approach is standard in control theory and is useful for determining stability of a system, for instance, in an amplifier with feedback. equals two-terminal component transfer functions equals, for two-terminal components the transfer function, or more generally for nonlinear elements, the constitutive equation, is the relationship between the current input to the device and the resulting voltage across it. The transfer function, Z, S, will thus have units of impedance ohms. For the three passive components found in electrical networks, the transfer functions are: for a network to which only steady ACK signals are applied, S is replaced with G per mil and the more familiar values from ACK network theory result. Finally, for a network to which only steady DC is applied, S is replaced with 0 and DC network theory applies. Equals to port network transfer function equals, transfer functions, in general, in control theory are given the symbol H, S. Most commonly in electronics, transfer function is defined as the ratio of output voltage to input voltage and given the symbol A, S, or more commonly, a, G per mil, so that the A standing for attenuation, or amplification, depending on context. In general, this will be a complex function of G per mil, which can be derived from an analysis of the impedances in the network and their individual transfer functions. Sometimes the analyst is only interested in the magnitude of the gain and not the phase angle. In this case the complex numbers can be eliminated from the transfer function and it might then be written as two-port parameters. The concept of a two-port network can be useful in network analysis as a black box approach to analysis. The behavior of the two-port network in a larger network can be entirely characterized without necessarily stating anything about the internal structure. However, to do this it is necessary to have more information than just the A, G per mil described above. It can be shown that four such parameters are required to fully characterize the two-port network. These could be the forward transfer function, the input's impedance, the reverse transfer function and the output's impedance. There are many others. One of these expresses all four parameters as impedances. It is usual to express the four parameters as a matrix. The matrix may be abbreviated to a representative element. Or just, these concepts are capable of being extended to networks of more than two ports. However, this is rarely done in reality because, in many practical cases, ports are considered either purely input or purely output. If reverse direction transfer functions are ignored, a multi-port network can always be decomposed into a number of two-port networks. Distributed components, where a network is composed of discrete components, analysis using two-port networks is a matter of choice, not essential. The network can always alternatively be analyzed in terms of its individual component transfer functions. However, if a network contains distributed components, such as in the case of a transmission line, then it is not possible to analyze in terms of individual components since they do not exist. The most common approach to this is to model the line as a two-port network and characterize it using two-port parameters. Another example of this technique is modeling the carriers crossing the base region in a high-frequency transistor. The base region has to be modeled as distributed resistance and capacitance rather than lumped components. Image analysis. Transmission lines in certain types of filter design use the image method to determine their transfer parameters. In this method, the behavior of an infinitely long cascade-connected chain of identical networks is considered. The input and output's impedances and the forward and reverse transmission functions are then calculated for this infinitely long chain. Although the theoretical values so obtained can never be exactly realized in practice, in many cases they serve as a very good approximation for the behavior of a finite chain as long as it is not too short. Nonlinear networks. Most electronic designs are, in reality, nonlinear. There is very little that does not include some semiconductor devices. These are invariably nonlinear. The transfer function of an ideal semiconductor p-n junction is given by the very nonlinear relationship, where I and V are the instantaneous current and voltage. I/O is an arbitrary parameter called the reverse leakage current whose value depends on the construction of the device. Vt is a parameter proportional to temperature called the thermal voltage and equal to about 25 MV at room temperature. There are many other ways that nonlinearity can appear in a network. All methods utilizing linear superposition will fail when nonlinear components are present. There are several options for dealing with nonlinearity depending on the type of circuit and the information the analyst wishes to obtain. Constitutive equations equals. The diode equation above is an example of an element constitutive equation of the general form. This can be thought of as a nonlinear resistor. The corresponding constitutive equations for nonlinear inductors and capacitors are respectively. Where F is any arbitrary function, I is the stored magnetic flux and Q is the stored charge. Existence, uniqueness and stability equals. An important consideration in nonlinear analysis is the question of uniqueness. For a network composed of linear components there will always be one, and only one, unique solution for a given set of boundary conditions. This is not always the case in nonlinear circuits. For instance, a linear resistor with a fixed current applied to it has only one solution for the voltage across it. On the other hand, the nonlinear tunnel diode has up to 3 solutions for the voltage for a given current. That is, a particular solution for the current through the diode is not unique, there may be others, equally valid. In some cases there may not be a solution at all, the question of existence of solutions must be considered. Another important consideration is the question of stability. A particular solution may exist, but it may not be stable, rapidly departing from that point at the slightest stimulation. It can be shown that a network that is absolutely stable for all conditions must have one, and only one, solution for each set of conditions. Methods equals. Boolean analysis of switching networks. A switching device is one where the nonlinearity is utilized to produce two opposite states. CMOS devices in digital circuits, for instance, have their output connected to either the positive or the negative supply rail and are never found at anything in between except during a transient period when the device is actually switching. Here the nonlinearity is designed to be extreme, and the analyst can actually take advantage of that fact. These kinds of networks can be analyzed using Boolean algebra by assigning the two states to the Boolean constants 0 and 1. The transients are ignored in this analysis, along with any slight discrepancy between the actual state of the device and the nominal state assigned to a Boolean value. For instance, Boolean 1 may be assigned to the state of plus 5V. The output of the device may actually be plus 4.5V, but the analyst still considers this to be Boolean 1. Device manufacturers will usually specify a range of values in their data sheets that are to be considered undefined. The transients are not entirely uninteresting to the analyst. The maximum rate of switching is determined by the speed of transition from one state to the other. Happily for the analyst, for many devices most of the transition occurs in the linear portion of the device's transfer function, and linear analysis can be applied to obtain at least an approximate answer. It is mathematically possible to derive Boolean algebras which have more than two states. There is not too much use found for these in electronics, although three-state devices are passingly common. Separation of bias and signal analyses. This technique is used where the operation of the circuit is to be essentially linear, but the devices used to implement it are nonlinear. A transistor amplifier is an example of this kind of network. The essence of this technique is to separate the analysis into two parts. Firstly, the DC biases are analyzed using some nonlinear method. This establishes the quiescent operating point of the circuit. Secondly, the small signal characteristics of the circuit are analyzed using linear network analysis. Examples of methods that can be used for both these stages are given below. Graphical method of DC analysis. In a great many circuit designs, the DC bias is fed to a nonlinear component via a resistor. Since resistors are linear components, it is particularly easy to determine the quiescent operating point of the nonlinear device from a graph of its transferred function. The method is as follows. From linear network analysis, the output transfer function is calculated for the network of resistor, S, and the generator driving them. This will be a straight line and can readily be superimposed on the transferred function plot of the nonlinear device. The point where the lines cross is the quiescent operating point. Perhaps the easiest practical method is to calculate the network open circuit voltage and short circuit current and plot these on the transfer function of the nonlinear device. The straight line joining these 2 points is the transfer function of the network. In reality, the designer of the circuit would proceed in the reverse direction to that described. Starting from a plot provided in the manufacturer's data sheet for the nonlinear device, the designer would choose the desired operating point and then calculate the linear component values required to achieve it. It is still possible to use this method if the device being biased has its bias fed through another device which is itself nonlinear, a diode for instance. In this case, however, the plot of the network transfer function onto the device being biased would no longer be a straight line and is consequently more tedious to do. Small signal equivalent circuit. This method can be used where the deviation of the input and output signals in a network stay within a substantially linear portion of the nonlinear device's transfer function, or else are so small that the curve of the transfer function can be considered linear. Under a set of these specific conditions, the nonlinear device can be represented by an equivalent linear network. It must be remembered that this equivalent circuit is entirely notional and only valid for the small signal deviations. It is entirely inapplicable to the DC biasing of the device. For a simple two-terminal device, the small signal equivalent circuit may be no more than 2 components. A resistance equal to the slope of the VI curve at the operating point, and tangent to the curve. A generator, because this tangent will not, in general, pass through the origin. With more terminals, more complicated equivalent circuits are required. A popular form of specifying the small signal equivalent circuit amongst transistor manufacturers is to use the 2-port network parameters known as H parameters. These are a matrix of 4 parameters as with the Z parameters, but in the case of the H parameters they are a hybrid mixture of impedances, admittances, current gains and voltage gains. In this model the 3-terminal transistor is considered to be a 2-port network, one of its terminals being common to both ports. The H parameters are quite different depending on which terminal is chosen as the common one. The most important parameter for transistors is usually the forward current gain, H21, in the common emitter configuration. This is designated HFE on datasheets. The small signal equivalent circuit in terms of 2-port parameters leads to the concept of dependent generators. That is, the value of a voltage or current generator depends linearly on a voltage or current elsewhere in the circuit. For instance, the Z parameter model leads to dependent voltage generators as shown in this diagram. There will always be dependent generators in a 2-port parameter equivalent circuit. This applies to the H parameters as well as to the Z and any other kind. These dependencies must be preserved when developing the equations in a larger linear network analysis. Piecewise linear method. In this method, the transfer function of the nonlinear device is broken up into regions. Each of these regions is approximated by a straight line. Thus, the transfer function will be linear up to a particular point where there will be a discontinuity. Past this point the transfer function will again be linear but with a different slope. A well-known application of this method is the approximation of the transfer function of a p-n junction diode. The actual transfer function of an ideal diode has been given at the top of this section. However, this formula is rarely used in network analysis, a piecewise approximation being used instead. It can be seen that the diode current rapidly diminishes to IO as the voltage falls. This current, for most purposes, is so small it can be ignored. With increasing voltage, the current increases exponentially. The diode is modeled as an open circuit up to the knee of the exponential curve, then past this point is a resistor equal to the bulk resistance of the semiconducting material. The commonly accepted values for the transition point voltage are 0.7 V for silicon devices and 0.3 V for germanium devices. An even simpler model of the diode, sometimes used in switching applications, is short circuit for forward voltages and open circuit for reverse voltages. The model of a forward-biased p-n junction having an approximately constant 0.7 V is also a much-used approximation for transistor base emitter junction voltage in amplifier design. The piecewise method is similar to the small signal method in that linear network analysis techniques can only be applied if the signal stays within certain bounds. If the signal crosses a discontinuity point, then the model is no longer valid for linear analysis purposes. The model does have the advantage over small signal, however, in that it is equally applicable to signal and DC bias. These can therefore both be analyzed in the same operations and will be linearly superimposable. Time varying components equals, in linear analysis, the components of the network are assumed to be unchanging, but in some circuits this does not apply, such as sweep oscillators, voltage-controlled amplifiers, and variable equalizers. In many circumstances the change in component value is periodic. A nonlinear component excited with a periodic signal, for instance, can be represented as a periodically varying linear component. Sidney Darlington disclosed a method of analyzing such periodic time-varying circuits. He developed canonical circuit forms which are analogous to the canonical forms of Ronald Foster and Wilhelm Kauer used for analyzing linear circuits. See also, Bartlett's bisection theorem, equivalent impedance transforms, Kirchhoff's circuit laws, mesh analysis, Millman's theorem, Ohm's law, reciprocity theorem, resistive circuit, series and parallel circuits, T. Legend's theorem, two-port network, Y-delta transform, symbolic circuit analysis. References. External links, circuit analysis techniques includes node mesh analysis, superposition, and Thevenin Norton transformation, nodal analysis of op-amp circuits, analysis of resistive circuits, circuit analysis related laws, examples and solutions, Samin Ahmed Khan, Set Theoretic Approach to Resistor Networks, Physics Education, Volume 29, Number 4, Article Number 5.